Hey guys, it's Malta here, and in today's video I'm going to introduce you to the derivative along with the tangent line problem. In this video I'm not going to cover any specific problems from the textbook, but rather I will just explain the principles behind the derivative and how it relates to our previous exploration of limits from chapter 1. In the future videos covering this chapter I will be presenting the commonly used derivative rules, but for now we're going to stick to the very basics. So without any further ado, let's get into it. So the first thing that I want to address here with the whole derivative and tangent line problem is the fact that this is all very similar to what we've been doing previously, or what you would have been doing previously, back all the way in Algebra 1 in which you were finding slopes. Because back then, what you were dealing with is something known as a secant slope. And so you'd be dealing with a secant line slope. And a secant line slope actually really just consists of the formula f of x plus delta x minus f of x. And that is all going to be divided by x plus delta x minus x. And this essentially here is rise over run. And if you were to simplify this down, this would just become, this is just equal to, obviously, f of x plus delta x minus f of x all over delta x. So that's what this simplifies down to. But this is, in a sense, rise here in the numerator over run in the denominator. And this formula is pretty much going to be pretty similar to how we're going to evaluate slopes of tangent lines, which is essentially what a derivative is. The derivative is essentially just looking at a function and saying, okay, at the specific point, the specific x value, what is the slope found on y? So instead of looking from, let's say, x is 4 to x is 10, we're going to be looking specifically at x is 5 and seeing what the slope right there is in fact. Now, I know this formula, some of you might be saying, oh, the secant line slope formula, I haven't really seen this before. And so I just want to explain how this formula exactly is sort of originated and how I kind of came to sort of discover it, per se. So basically, what happens is if I was to draw, let's say, this function here, let's say it goes like this, it's kind of like a parabola, this is pretty awful, but you can see it's a function like this, and yeah, there we go. Just trying it out. And let's say here's our axis, our x-axis, that is, and this right here is x, and this right here is x plus delta x. And let's say we're trying to find, like as we did before, a slope from, let's say, a point over here to a point over here, secant line slope, and we draw our line, so that'll go kind of like this, as you can see. So essentially this is kind of our secant line, and if we put in the coordinates here, just let's say this is going to be x comma f of x for this coordinate, and then over here on this coordinate we have x plus delta x comma f of x plus delta x. And that's for this point here. And this is for this point here. Yeah, there we go. So these are the coordinates of these 2 points that we're examining for the secant slope. And so as you can see here, this is rise over run, as I mentioned before in this formula. We have f of x plus delta x, which came from this second point, minus f of x, which is the y-coordinate of the first point, and then we're just dividing it by the x-coordinates of the second point minus the first. So this is what we've done before. This is secant line slope. However, we're going to investigate something else here, in which with tangent line slope, what's going to happen is we're going to say, instead of finding here to here, let's just find the slope of this tangent line that exists, let's say, right here. Let's find the slope of this tangent line. And I know this is messy, but essentially that's what we're being asked to do. We're being asked to find the slope right at this line. And when we're asked to find the slope, we are finding the slope of this tangent line. And this right here is called a tangent line. And so there we go. Now, with what's going on with the tangent line, there is another formula. So you have a tangent line slope formula. And for the sake of this, I know when we get further into derivatives, there's going to be all sorts of basic rules that make life really easy. But for now, we're going to keep it very simple and just stick with the complete basics. So we have the tangent line slope, formula that we have to keep in mind as well. So the tangent line slope formula, I just write this out. So then we have the tangent line slope as well. And this right here is going to be the limit as delta x goes to 0 of f of x plus delta x minus f of x all over delta x. So this right here is how we're going to figure out slopes of tangent lines. And essentially, this is essentially the same formula. There's just the difference here in the sense of we have a limit as delta x goes to 0. And some of you might be asking, okay, why do we have this limit as delta x goes to 0? Well, the answer is we're essentially saying we want to get as close to the value as possible. So when we're finding this tangent line slope, when we're finding the slope of this tangent line, we want to make sure that our change of x gets as close to 0 as possible. So essentially what's happening is before, we find the slope from 4 to 10. But now we're trying to find the slope at 5. So we're essentially trying to go to 5 to 5.00001. We're trying to get really, really close to 5. And so as a result, we want our change in x, so from 5 to 5.00001, to be as close to 0 as possible, because that'll give us the actual slope of the tangent line at that specific point. And that's kind of what we want to do. We want to make sure that the change in x from the first point to the second point when we're finding the slope is 0. And when we get into the derivative rules, we won't have to worry about any of these limits. But for now, this is something we have to take into consideration. And so the other thing, too, that I want to mention is specifically in terms of derivatives, there is a unique formula for them as well. It's slightly different from the tangent line slope, although it is, albeit, very, very similar. So I'll just write out for derivatives. So for derivatives here, we're going to have an equation that is the limit as h goes to 0 of f of x plus h minus f of x all over h. And so you can see in this case pretty much we've just replaced delta x with h, and this is sort of the customary formula that you're going to see used. Now, the one thing I will point out here is as we go down the road with this stuff, this formula here, f of x plus h minus f of x over h, is going to be very, very important. Because without the limit, this is actually the difference quotient or the slope of the secant. So that's what this would be called without the limit. But essentially, this is just sort of the derivative formula that we're going to be using for now. And in terms of this, these problems, I will say, using these sort of basic equations that we have, it's gonna take a long time. It's gonna be pretty laborious, but these equations really help to get us through and then make it such that by the time we get to the basic rules of differentiation that we're going to have, we can actually sort of understand the basic principles behind what we're exactly doing, which is really important when it comes to understanding derivatives and then later integrals. Because oftentimes people just know the formulas, but they don't exactly know how any of it, really in fact truly works. And that's why it's incredibly important, to be aware of what exactly is going on behind the scenes. So that's kind of what I want to point out. Now, with the other thing as well that I want to mention is derivatives do not exist at cusps. So I know a lot of times people think, oh, you can find a derivative, wherever there is, let's say, a limit, but that is not in fact true, because while we could find a limit, at a cusp, we cannot find a derivative at a cusp. So that's just really the one sort of, I guess, irregularity that exists between, tangent line, between like finding tangents, or I mean finding limits and actually finding derivatives or tangent lines, because at cusps you cannot find a derivative. So that's really the one sort of peculiar instance with derivatives that's important to remember, I find, in general. So yeah, and then the other thing that I want to say is this derivative formula, there's actually like another form that's used that you're going to see a lot, which is so the derivative of c, so this little tick mark here, this f tick mark, and then c, this means the derivative of c is equal to the limit as x goes to c of f of x minus f of c all over x minus c. And this is kind of the formula that we are going to be using time and time again. This one right here. So we're not going to use this tangent line slope formula that much, or this other formula over here. We're predominantly just going to use this formula, in part because this is kind of the one that in general proves to be the easiest and sort of makes the most sense. And so this is what we're going to use. So yeah. So I guess that's all there really is to say for this video. I know this hasn't been too much content, but this is just sort of the basic principles behind derivatives and tangent lines, and hopefully this was of some use. And if you like the video, definitely give it a like. And if you would like to see more content that I will be uploading in the future, I definitely would appreciate if you wouldn't mind subscribing. So once again, thank you for watching, and I hope to see you in the short term.